Hello everyone, today we'll be solving the problem number 406, queue reconstruction by height. So what the question states here, we are given an array of people. You can clearly see here, we are given an array of people where each person is represented by hi and ki. So this is hi, nothing but the height, their height, and this is ki. Ki is nothing but the number of people in the front of them who have height greater than or equal to hi. So this one, 0, what they have mentioned here, this is ki, which is number of people in front of hi. So it is number of people um, in front of them who have height are greater than or equal to hi. This should be greater than or equal to height greater than or equal to hi. So 7 in this case, again I am telling this one, hi, this one is ki. So hi is nothing but the height of the height, and 0 here nothing but the number of people in the front of them who have height greater than or equal to hi, right? So what we need to find out then, we need to reconstruct the queue based on these conditions and return it as ordered list. So we have to uh, reconstruct the queue based on these conditions and return it as an ordered list, right? That's what they have given here. Here, see here, they have given 7, 0, 4, 4, 7, 1, 5, 0, 6, 1, and 5, 2. So after reconstructing the queue based on the particular conditions. What was the conditions? Hi is the height and ki is the number of people in front of them who have height greater than or equal to height. These conditions, we need to reconstruct the queue based on these conditions and return it as an ordered list. So I hope this is completely clear. So here the output that we got here is 5, 0, 7, 0, 5, 2, 6, 1, 4, 4, 7, 1. Based on what conditions? Hi, which is the height, and based on ki is the number of people in front of them who have height greater than or equal to height. So this is the height. So they have given the clear-cut explanation. You can go with the explanation. Same goes with the example 2 as well. So I hope the question is completely clear. So just keep in mind we have two conditions, nothing but hi and ki. Hi is nothing but the height and ki is nothing but the this one, number of people in front of them who have height greater than or equal to hi, right? So we need to reconstruct the queue based on these conditions and return it as ordered list. So after reconstructing the queue based on the conditions that they have given, we have to return it as an ordered list. I hope the question is completely clear. So we saw that one with the example as well, right? So first what we will do, we will discuss the approach followed by the edge cases and finally write the code and discuss the complexities of the code that we have written. Initially, as usual, we'll be going with the approach, right? So for approach, I'll just be considering the same example, the first example they have given. Sorry. So this one I'll be considering so that it will be easier to understand, right? So let's discuss the approach initially. So let's discuss the approach step by step. So I have considered the same example, first example that is given in the question, same example. So first element that is present, suppose if you consider this one as x and this is y, x is nothing but the hi and y is nothing but the ki here. This one first element is considered as hi and second element in the this one array is considered as ki, right? So this one we have to keep in mind. So we will be making use of the Fenwick tree or the binary indexed tree to solve this problem. Again, I'm telling we'll be making use of the Fenwick tree or binary indexed tree to solve this problem. Just keep this in mind. So let's move on with the first step. So in the first step, what we would be doing here, we will sort the people array. When I say we will start the people array, we will sort the ki part. So this one, all the ki part here, this one. We will be sorting the people array. So this is height. This is the people who are standing next this one, people who are standing front of the hi, right? Front of the hi whose height is either equal or more than hi, right? So we are sorting the people's array means every second element that is present in the array. We are sorting this one. So just keep this in mind. We will sort the people array. Sort people array based on height in ascending order. First thing we'll do that. And if height is same, then we will sort ki in the descending order. So again I'm telling, just keep this in mind. This is very important. What we are doing here, we are sorting sort people based on height in the ascending order, nothing but hi. And if height is same, if the people height are same, then we will sort chi and ki in descending order. This is very important. So after sorting, our array becomes this one. So before this one, let me write it here itself. This is fine. So after sorting of the array, the array becomes this one. 4, 4 here, 5, 2, and 5, 0, 6, 1, 7, 1, and finally 7, 0. This is fine. What we are doing here, we are sorting people based on height in the ascending order, and if height is same, then we are sorting ki in the descending order. That's what we are doing here. You can clearly see here. I hope this is completely clear. 4, 4, this one. This is the array after sorting ki or sorting the people based on these two conditions, previous conditions. You can clearly see. Let's move on with the second step. Second step here is we are initializing a Fenwick tree here. So we will initialize Fenwick tree to track open positions in the queue. So we have to track all the open positions in the queue, right? For that one, for that purpose, we'll be making use of binary index tree or the Fenwick tree. Let's initialize the Fenwick tree here to track open positions in the queue. Initially, all the positions are available. Nothing but initially, all the positions are available. Nothing but Boolean value 1 in BIT. Initially, all the positions are available in the binary index tree. This is for the previous one, step 1, array after sorting, right? So in the step 2, we are initializing the Fenwick tree. Initially, all the positions are available in the this one binary index tree, nothing but Boolean value 1, because all the positions are available in the Fenwick tree. Let's move on with the third step. Third step, we have to keep this in mind. This is very important. We are inserting people into the queue using Fenwick tree basically here. So for each person, h comma k, hi, comma ki we are considering, right? For each person hi comma ki, we are finding the kth available position using binary search. We are finding the kth available position, whatever the available position after sorting. This is, so first step is we have sorted based on the people. That was two conditions. Those were two conditions if you remember previously. Second step was we initialized the Fenwick tree and all the positions were available in the queue, right? In the Fenwick tree. So how we are filling? It is based on the binary search. We are filling this one. For each person h comma k, we are doing it based on the binary search. For each person, we will find the kth available position using the binary search in the Fenwick tree. So this is very important. Next is, let's insert the person at the position and update the tree to mark it as occupied. After inserting the person at particular position, we have to mark that position as this one. We have to mark that position as occupied, right? Again, we cannot fill the h comma k at same position, right? So we are inserting the person at that position and we are updating the tree to mark it as occupied. I hope this is clear, right? This is the second step. So let's see the insertion process step by step. Initially, we have this array. Let's come to the step 2 here. Page 2, I think, page 3, sorry. So we have, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So let's go with 4, 4 initially. I'll just come here. Yeah. First, what we will be inserting? 4, 4 we had, right? So let's insert here 4, 4. So just give me a second here. let me do one thing. Let's change this one to yellow. So I'll just give here, let's insert 4 comma 4 here first. So we have the sorted array here. You can clearly see 4 comma 4 right here. So let's insert 4 comma 4 at index 4. So we are inserting this one 4 comma 4 at index 4. So this will be just give me a second here. This indexing starts from 0, right? 0, 1, 2, 3, 4, 5. So we are inserting 4 comma 4 at index 4 here. This one 4 comma 4. I hope this is clear. This is the first step. So the next this one h comma k, we have this one, right? So the next this one we have to consider here as 5 comma 2. Let me come here. Let's insert 5 comma 2 at index 2 here. So let's let's insert this one at the index 2 here, 4 comma 4 at 4, this one at index 2 here. Index 2 is this one right here. This one has to be 5 comma 2 now, 5 comma 2, and we already have 4 comma 4 here. This is fine. So the third step, we have to insert here this one, this pair 5 comma 0. I'll just come here. Let's insert here 5 comma 0. Let's insert here 5 comma 0. So this has to be at the this one at the index 0. You can clearly see here. This is at the index 0. So this will be 5 comma 0. We have sorted the people based on two conditions, right, that we saw. So we are consider after the array we got in particular order, right? So the elements we are taking from there itself. So this will be at the index 0. Next what pair we have to consider here? Next we will be considering 6 comma 1 here. Let me come here. Let me consider here 6 comma 1. So here we will be going with the index 3 here. In this case, we will be going with index 3. So we already have the 5, this one, right? 5 comma 2 and 5 comma 0. So 6 for this one will be going with index 3 here. So this will be, let me give here 5 comma 2 and 4 comma 4 here. This is fine. Finally, this one will be 5 comma 0, 5 comma 2, 4 comma 4. We are adding this one 6 comma 1 at index 3, 0, 1, 2, 3 here, 6 comma 1 here. I hope this is clear, right? We are inserting, now we have to insert 7 comma 1. So now we are inserting 7 comma 1. We are inserting this one at the index 5. So this one will be last. So here I can just write 5 comma 0, 5 comma 2, 6 comma 1 here, 4 comma 4, and we are inserting this one at the index 5, nothing but 7 comma 1 here. I hope this is clear. Only this is left now, right? Only this is left. So let me come here. So finally we have to insert here the last one that is left, nothing but the 7 comma 0 here. So let me insert 7 comma 0 here at the index 1. So here it will be 5 comma 0, 7 comma 0, 5 comma 2, 6 comma 1 here. This is fine. And 4 comma 4 and 7 comma 1, 4 comma 4 and 7 comma 1. I hope this is clear, right? So now the final output that we got here after the insertion process, first step was sorting based on two conditions that we saw. Second step was here we initialize the Fenwick tree. So this step, let me come here, this one. Second step was we initialize the Fenwick tree here. Initially, all the positions were available. Third step was for each person, we were finding the kth available position based on the binary search. This is very important. Based on the binary search that was available in the based on the binary search in the Fenwick tree. So insert the people at the position and update the tree to mark it as occupied. Once we insert the person at the particular positions, we are updating the tree as we have to update the tree just to mark it as occupied once we insert the person. This is very important. So we saw the insertion process here. This one was at index 3, this one was at index 5. Finally, this was at index 1. So the final output that we got here is this one. So first one is 5, 0. Second one is 7, 0. Third one is for this one 5, 2. Fourth one was 6, 1. And fifth one is for 4, 4. And the final one is for this one 7, 1. So this is the final output. This is same as the output that they have shown in the this one example, for the example 1. So this approach works absolutely correct in this case, right? So the approach works absolutely correct. So we went with the 3 steps: sorting, then we initialize this one Fenwick tree, and initially all the slots were available. And the third step we went with for each person we have to find the available position using the binary search. This is important in the Fenwick tree, and insert the person at the position and mark the tree to this one. We have to update the tree just to mark that one as occupied. Once we insert the person, we have to update it and mark it as occupied, right? So that we don't have to reuse that one again. So this one is the insertion process step by step we discussed. So the final output that we got is same as they had shown for the example 1. So the approach works absolutely correct. So let's discuss the edge cases one by one quickly. So now here all the people have ki, all the people have ki 0. This one people or ki is this one, right? We are considering the second element. When all the people have 0, this is already sorted by height. So the output will be same here in this case 5, 0. This one 6, 0 and 7, 0 in this case. This is same. This is already sorted by height. So the output is 5, 0, 6, 0 and 7, 0. So this is the output. Let's go with the second edge case. All people have the same height but different ki. Now what we will do, we will sort only by ki in this case, nothing but the people. This one will be sorting based on the ki or people. So output will be here based on the sorting of ki. Output will be 5, 0 first, then 5, 1 and 5, 2, right? This is fine. I hope this is completely clear. So only we are sorting based on the ki in the ascending order 0, 1, 2. You can clearly see here. This is for the second condition. All people have the same height but different ki. Let's go with the final edge case or the third edge case, large gaps in ki values. We have to ensure correct positioning here. So this one, for this output will be here 6, 0 and 5, 2, because 2 comes first after 0, and finally 4, 4. This is the output. I hope this is clear, right? So here all people have ki equals 0. All people have the same height but different ki. And the third one was for the third edge case was for the this one, large values in the ki values. So I hope all the edge cases are clear. Now let's start writing the code. So let's start writing the code. Initial step is we have to sort the people by height, nothing but the ascending order. If the people are of same height, or if the people are of equal height, then we will sort by ki, nothing but descending order, right? So that's one. How can we articulate that one in the form of code? People dot sort here, sort of ascending order, right? So this one will be a comma b, a minus b. I hope this is clear. This one ascending order of this one 0, a of 0 and b of 0. This one we have to mention this one clearly, right? So else if the people are of equal height, then we will sort by ki. So then we have to go with the descending order. So let's go with the ternary operator quickly. So this one is of b of 1 minus a of 1. This is for the descending order. Minus a of 1. Else we will go with a of 0 minus p of 0. I hope this is completely clear. Again, I'm telling, we are sorting the people by height, nothing but ascending order. If the people are of equal height, then we will sort by ki, nothing but the descending order. I hope the first step is completely clear. Second step was we had to initialize the Fenwick tree. Let's initialize the Fenwick tree. I'll just give you Fenwick or BIT, binary index tree, anything you can consider. I'll just give you Fenwick in my case. So new Fenwick tree of length of the people. I hope this is clear. So to use the Fenwick tree or to use the functionalities of the Fenwick tree, we have to build the Fenwick tree, right? So let's build the Fenwick tree very quickly. So I'll just consider class Fenwick. Yeah, trees here. Tree, sorry. So here class Fenwick tree I have given here. Let's go with the constructor, means initialization part, right? So here I'll pass n. So we are just passing n here. First, we'll be making use of one based indexing here. So one based indexing means it has to start with the indexing or index has to start with 1. So I'll just give here this dot n equals n. I hope this is clear. So the next step is Fenwick tree. We have to initialize the Fenwick tree array to 0 initially. So I just consider here this dot tree. Let's initialize this array of this dot n here, this dot n. Let's fill this one with 0 initial. So this is fine. Next step is we have to mark all the positions as available. Initially, we have to mark all the positions all as available. You know this one from the approach. We have discussed this one multiple times. In the step 2, if you remember, we initially all the positions of the BIT are available, right? We have to mark that all the positions as available. For that one, I'll just be making use of for loop. So I'll just give here let I equals 1. I then this dot n. Next I plus plus. Let's increment the I. So this is fine. Then we will update. So we haven't written the update function yet. We have to update the index, and initially it will be 1 as we are going with the 1 index. So we haven't written the update function yet. We'll be writing that one next. Let's go with the update method or update function here. So let me give here update of I comma val. This is fine. So first thing, let's make use of the simple while loop here. I less than n, or this keyword we have to use here, right, as we are going with the class. So first we have to update the binary indexed tree, right? So how can I articulate that one in the form of code? I can simply write here this dot tree of I equals I plus value we have to give here. As we are considering tree, this is iterated value of the tree plus val. So how can I write that one? So sorry, what did I do here? Plus equals this one, val. So I hope this is clear. Next step is we have to move to the next index after updating the current one, right? After updating the current this one index in the binary index tree. So we have to move to the next index. For that, just give here I equals I plus I, and negative value also we have to consider. So minus I. I hope this is completely clear. This is for the update function. Next, let's go with the prefix sum function. So I'll just give here prefix sum of I here. Let me give here prefix sum of I. Let sum equals 0. Let me give here. Initially we have initialized the sum to 0. So let me write the simple while condition here. While of not 0 here. We have to consider I think. Yeah, this is fine. While of I. So we have to compute the prefix sum here. We have to calculate the prefix sum, or we have to compute the prefix sum here. This will be sum equals sum plus iterated value of the tree, nothing but this dot tree of I. I hope this is clear. After computing the prefix sum, we have to move to the parent index. Again, same thing. I equals I minus I, and this time we have to consider negative value as well. So I'll just give here minus I. So what we are doing here in the line number 18, you can clearly see this one whatever I have written. Here we are calculating the prefix sum. After calculating or computing the prefix sum, we have to move to the parent index. That's what we are doing in line number 19. So let's return sum here. So we need sum here, right? So let's return sum here. In this case, this is it for the prefix sum function. So next, finally, let's go with the find position. I'll just give you a find POS short form, right? So I'll just give you a find POS, nothing but we have to find the particular position. So I have just passed the parameter k here. So this is completely based on the binary search. So if you remember in the approach, we said we have to. So after sorting, initially after sorting, we have to put the particular pair, this one, h comma k pair in the queue based on the binary search, if you remember. So we have to find the position in the queue based on binary search. That's what we will be doing here. So here let L equals 1, let me give here, R, right, binary search, left and right we are considering here. Simple, right? So this one, let's initialize R to last one, nothing but N. We are making use of this keyword because we are going with the class. So simple, while L less than R, then what we will do, let's calculate mid first. Mid equals L plus this one R minus 1. So this one, let's make use of the right shift operator here. This one, or you can just make use of this one as well. What do you call, mat.floor or double tilde operator as well, if you're not understanding this one. So you can just go with the mat.floor or double tilde operator of L plus R by 2. I'm just making use of the right shift operator here. Same functionalities. You can either make use of mat.floor or double tilde operator, or you can go in this way as well by making use of the right shift operator to find the mid. So here we are finding binary, we are making use of the binary search to find the mid value, right? So next, let's make use of here this dot, let's go with the prefix sum here. So let me copy paste same thing here, prefix sum of mid. If it is greater than k, then what we will do here, just give me a second, right, we will assign right to mid, else we will assign left to mid plus 1. Pure binary search right here. So you can clearly see this is nothing but binary search. So let's return left here, right? This is it for the find position, this one, what do you call, find position function or method. So let me format this one once. So this is it for the build. This is it for the build, right? So next, let's move on with the next step within the main function. Let me come to the main function now. So we have built the Fenwick tree successfully. Let's move on with the next steps. So initially we sorted here based on the position, I mean based on the condition. We know this one. We have initialized the Fenwick tree here. Next step is we have to create an empty array for the result. So we need the result, right? So we have to store the result somewhere. For that one, we are creating the empty array, right? So I can just give here, let result equals here new array of here people dot length. I hope this is clear. So the next step here will be we have to insert each person at correct position. So each person we are inserting at correct position means we have made use of the binary search. So for the insertion, we are inserting at a particular place by making use of the binary search. So here in the step 4, what we are doing, we are inserting each person at correct position. We saw that one during the approach, inserting particular h comma k at particular index, right? At the particular index. That's what we were doing initially. So finally we got the particular output, right? Correct output. So that's what we'll be doing in the step 4. Let's insert each position at each person at correct position here. So I'll just make use of simple for loop here. Let individual p of people here. So here let's find the correct position first. So for position, we can just go with the find. We can just make use of the find position, this one here, right? Find position function within the fenwick tree class. So I'll just give here fenwick dot. Let me copy this one here. Find position based on the binary search we are doing here, right? So this one has to be p of 1. What we are doing in this line? So we are just finding the correct position for the particular people to insert, right? So next, let's place the person in the result array. How can we place the person in the this one in the result array? Result of position we have already considered, this one. So position minus 1. So this one we will assign this one to p. So I hope this is clear. We are just placing the person in the result array. After placing the person in the result array, we have to mark the position as occupied. This one we saw only 2 conditions for that. First one is based on the binary search, we were inserting the person. Then after we did that, we have to mark that particular position as occupied, because we have to avoid the reuse of that one, right? We have to avoid the reuse. So we have to mark the position as occupied. So for marking the position as occupied, we have to make use of the update function here. So here I'll just give fenwick. So let me paste here update position comma minus 1. So we have just marked the position as occupied here. I hope this is clear. So the next step here is finally we have to return the reconstructed queue. So in our case, we have to just return result. So we have considered a result variable here, right? We just have to return the result. I hope this is clear. I hope this works, man. Let's see. Let me hit the run button. So here we have this one, unexpected identifier tree. So we have to go with the this one. I don't need space here, right? So let me hit the run button here. So wrong answer we are getting. So let's check where we have done. So what are the wrong things that I have done here is in the line number 3, if you would have heard me correctly, I said we will be using 1 based indexing, right? So here I forgot to give n plus 1. So indexing starts from 0. When I said we will be making use of 1 based indexing, we have to give here n plus 1, right? We have to initialize n to n plus 1. So here I forgot n plus 1. This is one mistake. So I'll just come here in the line number 27 while calculating mid. So we are making use of binary tree here within the fenwick tree class, right? So while calculating mid here, this has to be right minus left, not right minus 1. So this is one thing. In a hurry, I mistyped. I gave 1 here, I think. This is fine. The final thing is here as well. So if the person, if the people are having the equal height, then we are going with the this condition, else we are going with this one, right? So here instead of minus, equal height means we are comparing. So this should be triple equals, not minus here. So these are the mistakes that I have done. So let me do one thing here. Let me format the code once and let me hit the run button. So here now you can clearly see all the sample test cases are getting passed here, right? So I'll just hit the submit button quickly. So I hope this works. Let's see. So you can clearly see all the test cases are getting passed here. So the code works absolutely correct in our case. So whatever the code that we have written, the code works absolutely correct. So let's quickly discuss the complexities of the code that we have written. So what is the approach that we went with here? We went with fenwick tree with binary search for find position. Here you can clearly see for the find position function we have went with binary search. So the main thing here is we went with fenwick tree. So we went with the approach Fenwick tree. So what would be the time complexity here? The overall time complexity would be big O of n log n. So why here the overall time complexity here is big O of n log n? Because here we have made use of the sorting in the first step itself in the main function. You can clearly see here, right? So we have made so we have used sorting, right? We have made use of the sorting. So the sorting is the dominant factor here. So the overall time complexity would be big O of n log n. So what would be the space complexity here? The overall space complexity would be big O of n here. So why here this one space complexity here is big O of n? Because so again, here why the space complexity here is big of n? Because we are making use of the Fenwick tree of size n plus 1. You can clearly see one indexing, one best indexing we are going with, right? So here they are making use of the Fenwick tree of size n plus 1 and result array. In the main function, we have made use of the result array, right? Result array of size n, both requiring big O of n space. So overall space complexity would be here big O of n, right? So overall time complexity would be here big O of n log n, and the space complexity would be big O of n. So one thing I just wanted to discuss here, why we are making use of Fenwick tree. We would have went with other data structures as well, right? Why we are making use of Fenwick tree here? Because Fenwick tree basically it helps us to manage the positions in the queue by making use of the binary tree here. You can clearly see we made use of the binary tree inside find position function here. So basically Fenwick tree helps efficiently manage positions in the queue. That's the reason we went with the Fenwick tree. Also here we went with the sorting. You can clearly see sorting basically it ensures correct order, right? Basically it allows us to place the elements without having to backtrack. If we went with backtracking, then it would have been brute force. So overall time complexity would have been big O of n square. We should have made use of array dot splice in that case, right? Instead of making use of array dot splice, and instead of going for the backtracking, overall time complexity would have been big of n square. So instead of that, we can make use of the we made use of the Fenwick tree to find the available positions. So to find the available positions here, we are finding the available positions within the time complexity of big of logarithmic n. As we had made use of the this one sorting, which plays a dominant factor, final overall time complexity was big of n log n, right? We can just this one find the available positions in big O of logarithmic n. So in this case it is better to make use of the Fenwick tree. It avoids backtracking as well as it avoids array dot splice. So overall time complexity would be big O of n log n rather than big O of n square. N log n is far better than big O of n square, right? So that is the reason it is better to go with the Fenwick tree for this particular problem. So I hope the this one the solution what we have written is completely clear. For now this is it. Thanks for watching, guys.